The individual steps of any given mass balance problem are not usually too hard. They're algebraic or arithmetic, but knowing where to start and how to use the information that you're given can be a challenge. To show an example of how you might take apart a problem that's complex, I'd like to do a balance on a system that has a reaction and a reactor and a separator. And so this video is on the topic of balances on multiple units. This is the example that I'd like to do. As usual, we'll read through it carefully to see what the problem is. Propane is dehydrogenated to form propylene in a catalytic reactor. Reaction given and balanced. The process is to be designed for a 95% overall conversion of propane. The reactant products are separated into two streams. The first, which contains hydrogen gas propylene and 0.555% of the propane that leaves the reactor, is taken off as product. The second stream, which takes the balance of the unreacted propane, 5% of the propylene in the product stream, and no hydrogen, is recycled to the reactor. Calculate the flow rates and compositions of all streams and the single-pass conversion of the propane in the reactor. This is a complicated problem to read. There are a lot of pieces of information, unusual pieces of information about how the splitting occurs. And it's really hard to see what this problem is. If someone had drawn the flow diagram for us, it would be a lot clearer. That's not given in this case. And so we need to read the problem statement very carefully to know what to draw. So we'll read it again, emphasizing the important parts. We have a reaction going on. We have one reactant and two products. Then there is a separation into two streams. One stream has three components, hydrogen, propylene, and propane. And the second stream, which has propane and propylene and no hydrogen, and it's recycled to the reactor. So to draw this problem, we need a reactor and a separator. So we know this is going to be a little tricky, so we'll give ourselves lots of space. And we'll draw a reactor and a separator. The feed to the process is propane. And it goes into the reactor. The products from the reactor go to a separator. The separator separates into the product stream and to a stream that is recycled to the reactor. Now, this seems like what the problem is about, but actually this is not a helpful way to draw this problem. The problem is about a reactor separator, and it does recycle back. It says here that it recycles back to the reactor. But in order to do the balances, we're going to want to move this stream not to the reactor, but to a mixing point ahead of the reactor so that we can figure out what kind of mass enters the mixing point, comes from the recycle, and enters into the reactor. So that's an easy point of error. We're just going to start over with our reactor separator and include the mixer this time. So there's going to be a mixing point, which we're going to draw as a unit. Drawing the mixer as a unit helps us to make sure that we do those balances as we need to. So this is the fresh feed. It goes into the mixing point and meets the stream that is separated out and returned to the reactor. So let's try it this way. Reading the problem again. propane is dehydrogenated to form propylene in a catalytic reactor. So the feed, the fresh feed, is C3H8. And in the product stream, we're going to have some of the reactant, because not all is converted. So we're going to have C3H8. And we're going to have the two products, C3H6 and H2. The process is designed for a 95% overall conversion of the propane, meaning overall, when we put a hypothetical box around all these units, 95% of the propane is converted. The reaction products are separated in two streams. The first, which contains hydrogen gas, propylene, and propane, that's the one we've drawn, leaves the reactor and is taken off as product. The second stream, that's the one leaving the separator here, contains the balance of the unreacted propane and 5% of the propylene in the product stream and no hydrogen. So this has C3H6 as well. Calculate the flow rates and compositions. So we have propane coming in. We have recycled propylene coming into the mixing point. Before the reactor, we must have C3H8 and C3H6 both going into the reactor. Coming out of the reactor, we have C3H8 because there's not complete conversion. We have the two products, C3H6 and H2. They go into the separator. The separator separates out all of the hydrogen and some of the propane and propylene and sends back the unreacted propane along with some propylene into the mixing point. The problem statement also gives us two pieces of information. It tells us that 0.555% of the propane that leaves the reactor is taken off as product. And it tells us that 5% of the propylene in the product stream, that amount of propylene is represented in the recycle stream. So those are two facts that we have to read very carefully, translate into a mathematical expression, and then use to solve the problem. This problem doesn't give us any kind of molar flow rates to work with, so we can assume a basis. And so we'll assume a basis of 100 moles entering the fresh feed. Having assumed this basis, we can use this first fact that 95% overall conversion takes place to figure out what comes out of the process overall. The easiest way to see this calculation is to redraw the overall process so that we don't get too cluttered here. So let's draw the overall process as a single unit with 100 moles of our propane coming in, and the outlet stream, which has propane and C3H6 and hydrogen. And there is 95% conversion on this overall process. Now, in order to interpret that number, we need to know what conversion means. 95% conversion means that 0.95 is the ratio moles reacted over moles fed. Our reaction was given in the original problem statement. So our reaction is C3H8 goes to C3H6 plus H2. And I like to use the extent of reaction when I do reaction problems. And in terms of extent of reaction, moles reacted is the stoichiometric coefficient of the quantity of interest times xi, the extent of reaction. Moles fed was 100. And so the extent of reaction for the overall extent of reaction is 95 moles. Again, using the extent of reaction methodology, we can write in terms of extent of reaction all of the entities in the product stream. And so there is the stoichiometric coefficient times xi moles of, it equals the moles reacted. So we started off with 100 and we lost xi moles of propane. We gained xi moles of propylene, and we gained xi moles of hydrogen. So we have 95 moles of 5 moles of propane exiting the reactor. 5 moles. We have 95 moles of propylene, and we have 95 moles of hydrogen. So we've done the overall balance on the process, and we've got all of, in terms of our basis, we have all the flows at the exit of the process, and we can transfer those numbers back to our original sheet. So we have 5 moles of propane and 95 moles each of the other two reactants products. So we've used the first fact that was given to us in this problem, which is that the overall conversion of propane was 95%. We have another fact here. It says this fraction of the propane that leaves the reactor is taken off as product. So I'm going to take this percent and convert it into a fraction. So it's 0.00555 equals the ratio propane that leaves the reactor taken off as product. So we need the moles taken off as product divided by the propane that leaves the reactor. Propane that leaves the reactor is this stream. I'll call this Q1. And so, reading again, 0.00555, that fraction is that portion of the propane that leaves the reactor is taken off as product. So here is the amount of propane that's taken off as product, 5. 5 moles is taken off as product compared to the moles leaving the reactor, and that ratio is 0.00555. And we can solve for Q1. And we get 900.9 moles. However many significant figures we may have in this calculation, we'll wait to the end to truncate. For now, we'll carry extra digits so that we have complete accuracy. So Q1 is known. Normally, I would have space to write that flow right here on the flow diagram, but I'm not going to clutter this up at the moment. All right, so that was our second piece of information, and we have one more. 5% of the propylene in the product stream is recycled to the reactor. 5% of the propylene in the product stream is recycled to the reactor. Here's the propylene in the product stream, 95 moles. 5%, a quantity equivalent to 5% of the propylene in the product stream is recycled into the reactor. So here's the amount of propylene, I'll call it Q2. Q2 is equal to 5% of the propylene in the product stream. So now we also know Q2. Now that's all of the information that was given to us in the problem. We've translated it into information on our flow sheet. And we're being asked to calculate all the flow rates and compositions and the single pass conversion of propane in the reactor. So it's time to look closely at the kinds of balances we might be able to do and to move the information that we have around the flow diagram. So we can do balances on the separator, on the reactor, and on the mixer. We've already done all the balances on the overall reaction, overall process. So we can look here at the separator and see that we have a lot of information that we could use to make balances. To see them a little more clearly, I'll copy them over to a separate drawing of the separator. So here's what we know at the separator. Excuse me. We have Q1, which is 900.9 moles of C3H8. We have C3H6, and we have H2. Coming out of the separator, we have 5 moles of C3H8. We have 95 moles of C3H6, and we have 95 moles of hydrogen. Also coming out of the separator is some unknown, I'll call it Q3 moles of C3H8, and Q2 moles, which is given, which I know already, so I'll put the actual number here, 4.75 moles of C3H6. So writing it again, we can see that our balances are not too difficult here. Hydrogen is a tie component. It comes in one place and goes out another. So if 95 moles of hydrogen come out here, 95 moles of hydrogen must have come in here. So that's the hydrogen mole balance. On C3H6, we know 2 out of the 3 streams, so we can do the propylene mole balance. In is, let's say, Q4. Q4 in equals 4.75 out here and 95 out there. And the two together give us our final number. And on C3H8, we can do the final balance on the separator. We'll do the C3H8 balance. We'll say C3H8, 900.9 go in, Q3 come out, and 5 come out. So transferring these numbers back to our original flow sheet, we learned that the C3H8 stream was 895.8. Excuse me, 0.9, that's a typo on my other sheet. The Q2 is 4.75 moles. Here the Q1 is the flow rate of the C3H8. That one is 900.9. The C3H6 is 99.75 moles. And the hydrogen is 95 moles. We now have to do balances on the mixer. We can do these in a straightforward manner. C3H8 comes in 2 places and comes out here. 100 moles come in. 895.9 come in here. So 995.9 must exit the mixer. For the propylene, none come in here. It's a tie component. So what comes in from the recycle stream, 4.75, must be the number of moles that enter the reactor. We're getting close to the end. We actually know all of the flow rates. We just need to calculate the single pass conversion across the reactor. So to give ourselves again a little bit more breathing room, let's redraw. We have a reactor. Coming into the reactor, we have 995.9 moles of propane. And we have 4.75 mole of propene. 6. Coming out, we have C3H8 900.9, C3H6 99.75, and H2 equals 95. To calculate the single pass fractional conversion, we can use the extent of reaction for the single pass. And so that tells us that this quantity, we know that there is no hydrogen coming in, 95 come out, and so that means 95 must be the single pass conversion. So this is equal to the single pass extent of reaction, and the single pass fractional conversion is equal to moles reacted over moles fed. The moles reacted is again equal to that single pass extent of reaction. It's the same for the propane, and the moles fed of propane is 995.9, and so the single pass fractional conversion is calculated as .0954. So we now have all of the results for the problem, and we could calculate from the final molar flows here what the mole fractions are in each stream and any other questions that might be asked for this problem. So in summary, although a long problem, the key steps to solving this problem were to read the problem many, many times, to be very careful in drawing the units that are in the flow chart, including what compound goes in each stream, and then finally to use the bits of information that are supplied by the problem statement or that are known, and each one of those can be used to get to a fact that we needed to perform the mass balances.